Hello everyone, welcome to this video where we will discuss quantization simulation in AIMET. My name is Abhi Khobre. I'm from Qualcomm AI Research. AIMET stands for AI Model Efficiency Toolkit, and AIMET is an open source library brought to you by the Qualcomm Innovation Center. So in this video, we are going to cover quantization in AIMET. Specifically, we will cover the quantization simulation part of AIMET. If you have not had a chance yet to watch the introduction to AIMET video, I would highly encourage you to go back and watch that before you watch this video, because the introduction to AIMET video would give you some background context for this video. So let's dive in. So before we start, let me motivate to you like why use quantized hardware. So generally, by default, most machine learning models out there in the world, in the cloud or on your desktop, they run as floating point, generally 32-bit floating point on 32-bit floating point hardware. And instead of running on that hardware, if you convert the model and have it run on an integer hardware, and specifically a low precision integer hardware like 16-bit integer or even 8-bit integer, you get dramatic gains in power efficiency and also in compute, latency, so on and so forth, and also the memory that you require to store the model. So the question now is that most people believe that if you take a 32-bit floating point model, that's a high precision model weights and parameters that it has learned, and if you now try to execute that as with 8-bit integer operations, you're going to lose a lot of resolution and the accuracy is going to take a huge hit. And that's where AIMET comes in. So AIMET provides these techniques to help you run a lot of different variety of models down to the 8-bit precision, but also lets you control the precision on a per layer basis if necessary. So before we start understanding how quantization simulation in AIMET works, let's try to understand what are the use cases for this feature. And one use case is you can simulate the effects of quantization on off target, meaning like you don't have to run your model on target to understand how it would behave if run in low precision integer hardware. And so this is the first of the use cases. So the way this works is you take your trained model and you run it through AIMET, which will result or provide a simulation model. We'll look at the details of this. And then you take it through your evaluation pipeline, and the accuracy that you would get is now a simulated accuracy to simulate the effects of quantized integer hardware. The second use case is very similar to this. So while this simulation model can simulate the noise and help you understand, what is the accuracy that you're seeing or you would see on quantized hardware, you can now also take it, instead of an eval pipeline, take it through a training pipeline through a process called fine-tuning. And this what the model would do is, when you're training, the model in the forward pass is seeing this quantization noise, and in the backward pass, it'll try to learn and try to counteract the effects of this quantization noise. And so your model becomes more robust for quantized hardware, and it improves the accuracy on quantized hardware. This fine-tuning does not need like a full training. So it's not like, let's say you have models that may need 150, 200 epochs to train. This kind of fine-tuning may require a fraction of those epochs, on the order of 5 to 10 to 15 epochs, something like that. So let's, given these two use cases, let's jump to what quantization simulation does. Okay, so this picture tries to explain where does this quantization noise come from. What does this mean? So you have on this orange bar over here, pretend that this is a floating point kind of scale. It looks like a scale, and I think it's not. Floating point numbers can have a lot of resolution. This is just pictorially depicting that. So there's a lot of resolution, as you could see with these gray bars. Whereas if you convert this, some number which is on this scale to a number which is on an 8-bit integer scale, now an 8-bit integer can take 2 raised to 8 or 256 different values. And each of these 256 values would have a corresponding floating point number. So as you can tell that from this high resolution scale, we are only picking 256 numbers, and they correspond to this lower precision scale. So what we mean by quantization noise is if you took a number that is not directly mapped, like this point over here, then when you convert it to an integer number, it's gonna get rounded up to the nearest integer number, either this or this. In this case, it got rounded to this number. And when it gets rounded back, or when you start using it, now the value corresponding to this number is really this point in the scale. So you have incurred a noise going from what was originally this number to in effect going to this number. And this is where the quantization noise comes in. So every tensor, every value that you see in a tensor is going to have this quantization noise. And then when you do your mathematical operations on these tensors, that noise will get multiplied and propagated through the layers. And at the very end, you would see an effect on the accuracy of the model. Okay. So how do we simulate this noise? So what AIMET would do is, the first thing is it would place ops, and we'll look at some details, but it would place like ops after every layer or after every parameter, and these ops would capture the data as it's flowing through the model. So you would pass some representative data through the model. This is trying to depict a model. And so if you think about it, like for different layers in the model, it'll capture the data and it'll try to build a histogram with that data. So having built this histogram, now you have a few choices. So you have specifically two techniques in AIMET. One is called TF and one is called TF enhanced. And what TF does is very simple. Once you have the histogram, it finds the absolute minimum and maximum of this histogram, and that becomes the range of values that your integer would take. So essentially we would take, this is the range of numbers or 256 numbers that you have to play with. Let's say if you were uniformly distributed around 0, then you would, half of the numbers would lie to the on the negative part of the scale, half of the numbers would lie on the positive side of the scale, and the range would be determined by the range that you have captured. TF enhanced does very similar to that. It still builds a histogram, but what it would try to do is it would try to clip some of the outliers, and it would try to choose like a smaller range. So think of this layer over here. Let's say there were, while it's hard to see, let's say there were values all the way from this point to that point, but they are very low incidence of those values, whereas a lot of numbers are in this middle chunk. So with TF, you're going to pick these absolute min max, but with TF enhanced, you would pick, you would ideally clip off everything other than this blue part you're seeing. And so what you get is you get much more resolution over this blue part, and consequently the noise over this blue part has reduced, and the noise over this part has increased quite a bit, but there is such a low incidence of these numbers that it does not matter. Okay, so how does practically, how do we achieve this quantization simulation? So what would happen is, if you had a layer, what AIMET would do is it would place these logically, it would place ops called quantize and dequantize. So quantize means you go from floating point numbers to an int8 representation, and dequantize would go from an int8 representation back into a floating point representation. So it is roughly doing what this picture showed. It's going from a floating point number to a fixed point number, 8-bit number, let's say, and then it goes back dequantized to a floating point number. And so it is essentially simulating the effects of noise for each tensor value in these parameters. And same thing it would do on the output, and you could also simulate the same thing on the input of the layers. So you have all these choices. Now it is not necessary for you to actually simulate noise at every point. For example, if this layer fed into another layer, there is not much point going quantize, dequantize on the output and also on the input. So generally only the output quantization is enabled, if you may, and the parameter quantization is enabled. So this is how things work in the forward pass. As you see the data flow through, it's going to see this noise get introduced through the parameters and through the output. So note that the layer itself has not changed. And so because of that, AIMET can work on a variety of layers, including, this layer could be a custom layer, and it would ideally work without actually needing to know what this layer is doing, because the layer continues to operate in floating point. It is oblivious to what's going on outside, and these operations are just simply introducing or simulating the quantization noise. So what happens in the backward pass? In the backward pass, these operations over here, they act as straight through on the backward pass. So there is the gradients flow straight through without any impact back. And so the reason for doing a straight through back prop is so that you can have these parameters learn. So what would happen is you're still let's say you are training this model. On the forward pass, you would see the noise, and then when in the backward pass, you would take your prediction and calculate a loss, and then you would start, the model will try to learn to reduce that loss. And so these parameters would start getting trained to counteract the effects of this quantization noise that is there in the forward pass. And this helps improve the accuracy of your quantized model. So having said this, let's jump into some coding examples on how we can use quantization sim in AIMET. So let me switch to my code editor. Okay, so here we start with an empty window. So let's start getting some imports in. So I have imported a torch. We are going to start with a PyTorch example, and then torch vision, and then we have some pipelines for evaluation and training. So to start using AIMET quantization sim, we will first import the quantization sim, something called a quantization sim model. Okay, so let's start by instantiating a model. Today we are going to use the ResNet 18 model from Torch Vision, and we will get a pre-trained model and have it run on a GPU. So before we do anything, let's try to get a floating point accuracy, right? The accuracy of the model that you generally see. And so in our pipeline, we have an evaluation routine. So let's use that. So I'm passing it the model. I'm saying none, meaning use all of your evaluation data set to figure out the evaluation. And the last parameter is to say that this runs on a GPU. So once we do that, let's print out this accuracy. I'm gonna copy over some pretty formatted code here, and now we are going to instantiate this quantization sim model. So given the model, we are going to create a quantization sim model out of it, and I'm going to use the defaults here, but we will go back and look at all the parameters that we have for while creating this simulation model. And once we get the simulation model, let's try to print out the model and let's see what happens here. So I'm going to run this by itself for now. And let's take a look here what happens. So this evaluation will take a little bit of time, I think on the order of 10 seconds or so. And now we have evaluated or gotten the floating point accuracy, and so that was 70.15%. And then we created a simulation model, and now we are printing the simulation model. And so let's see what has happened to the model. So this is a ResNet 18 model. So it has, convolution 1, batch norm, ReLU, max pool, then goes into these layers and blocks. And then within the blocks, there is generally a convolution BN, ReLU, convolution BN kind of pattern, and so on and so forth. So what you would notice is right away, each of these layers has been wrapped with something called a post-training wrapper. And this post-training wrapper is going to essentially hijack the input before it goes into the layer and the output before it goes to the next layer. And it can also hijack the parameters. So essentially what it would do is, while in the forward pass, while data is flowing from this BN1 into this ReLU, it would take the input. If the input quantization is enabled, it would do the quantize dequantize operations on the input. Same thing, it can do the quantize dequantize operations on parameters. ReLU doesn't have parameters, but if you did on a convolution, it would do that on the parameters of the convolution. And then the same thing on the output, it can do, once the layer is executed, then it can do the quantize dequantize operations on the output as well, right? So this just keeps repeating for all the layers, and that's how you get your quantization noise. So now, so far we haven't really done anything. So the next call that we would do is we are going to call something. We are going to make a call to compute what we call encodings. And encodings are those sort of min-max parameters that we had seen. So if you go back to this picture, encodings are like the min-max variables that we see. And we are going to determine this through the layer. So to do that, we have to pass some data through this model. And then once the data has passed, then we can build these histograms. And then with the histograms, we can find the min-max. So let me go back to the code. So, so to pass data through the model, we need like a callback method that AIMET would invoke to pass data through the model. And so what we are doing is, in this case, we are going to, I'm going to copy over some code and then talk to it. So we make this call called compute encodings. And what this call is going to do is you pass it a forward pass callback and some arguments to this forward pass callback. This particular parameter just reflected back into the callback. So it could be of any type, right? In this case, it is an integer for iterations, but it could be an object, it could be anything you want. And so this lets you pass, very sophisticated parameters to your forward pass callback if you needed to. And so while a forward pass callback what it would do is it would take data from a data loader and pass it through your model. You don't really need to evaluate per se. You're just passing data through the model. But in this case, I am trying to adapt. So I created this sort of adapter, and I'm just going to use my same evaluation routine. I don't care about the accuracy that it returns, but an evaluation also does forward pass. So this is a strategy that you could apply, or you could write a separate forward pass callback as well, right? So I just did this and I adapted. So once the compute encodings runs, and this takes a little bit of time to run, then what we would do is we would run another evaluation on this sim model. And now what you're going to see is we are evaluating on the sim.model, not evaluating on model. And so this call by itself is going to create a copy of this model for the to add simulation option. And so when we evaluate the sim model, now we're going to see these effects of quantize, dequantize operations coming into play. And this accuracy is going to be lower accuracy compared to this floating point number. So let's run this, and it's going to take a little bit of time to run, like on the order of a few minutes. So I'm going to pause the video and then resume once it resumes. So let me kick it off. So it's going to start running. We can take a look at what it's doing. So I think it's passing data through the model at this point. So see you in a few minutes. Hey everyone, so welcome back. This has finished running. So the way we look at this is, if you remember, we started out with the model and the floating point accuracy was 70.15%. And after we are done quantizing, the int8 or the simulated accuracy is 69.05%. And so it's not a big drop in accuracy, it's about like a little over a percent drop. ResNet-18 is a fairly robust model from a quantization perspective. So in general, we see much lower drops in accuracy for ResNet-18. So, okay, that's pretty good. So if we go back to our code, so we created a simulation model, given a model, and we computed some encodings and then did a quantized evaluation. So this is the use case number 1 that I talked about. And use case number 2 is as simple as now invoking our training pipeline. And in this case, we would, let's say, train this model, let's say for 5 epochs. And that is it. That's use case number 2. You train the model and the model gets better. So you would say, okay, now once you have trained the model, you saw all those wrappers in the model. What happens to them? Can they run on target, for example, or can we actually run with those wrappers? And so you're correct. We need to remove those wrappers. And so there is an API provided in AIMET to export out the model. So you can just simply say, take that simulation quantization sim model that you have and just export it out to this location over here, give it the input shape, and that's it. What it would do is it would export out a PyTorch model. We started with a PyTorch model, you get back a PyTorch model. It would also export out an Onyx model and also export out in a JSON file all the min-max, those encodings that we had determined per layer and per parameter. So that's as simple as it can get. So let us dive a little bit into what are the knobs here, right? So let me bring up the API guide for this quantization sim API, sim model API. And while we, most of these parameters have defaults, and so we just had to say quantization sim model, but there are some knobs. So what are the knobs? So the first thing is this quantization scheme, which is this choice between TF or TF enhanced. And by default, it is set to TF enhanced. The second mode is for rounding, like do you want nearest rounding or stochastic? And by default, it's set to nearest. Then you can choose bit widths for activations or bit widths for parameters. They default to 8 bits, and that's what we got. But you could change it all the way from 4 bits to 31 bits. And while it's unlikely that you would have hardware to run with, let's say, 13 bits of quantization, but you could try it out and see what would happen if you ran on 13-bit hardware, right? For example, that was just a joke. But you can choose different bit widths to use. So for example, you could say what would happen if I ran this with 16-bit integers instead of 8-bit integers, and you can see that difference. This next flag is here for in place. So by default, this is true. So meaning you give it a model, create a copy of the model to add the simulation ops. But if you didn't want to do that, you could set this to true, and then it would just add the ops into the model that you passed in. And then there are input shapes, and there is a configuration file that we will perhaps not go into it in this video. Okay, so there's a whole bunch of parameters that you can choose to, so that gives you a little bit of choice, but actually you can do a lot more than this. So let's go back to the code and let me explain what I mean by that. So what I'm gonna do is I'm gonna put a breakpoint right there and try to stop at that breakpoint. And what I want to do is start a shell at that point, so we can take a look at some of what the simulation thing is doing. So let me create a console. Let me create some space for myself, and let me increase the size of this. Okay, so we have a simulation, and the simulation, it's a simulation model. So if you had a sim.model, you can print that out, and this is what we had seen. Now, let's pick on a layer in here, right? Let's say we pick layer, let's say 1, 0, con 2, right? Let's pick this layer for no reason. I'm just picking on a layer. So the way you look in the original model, the way you look at this layer is you do layer 1, 0, con 2, right? And so this is a convolutional layer in the original model. Now in the simulation model, you can repeat that, and now instead of it being a convolutional layer, you are going to see that it's a wrapper. Okay, and you can still get to the convolutional layer inside it through, it's wrapped inside it. So it's basically there's a module to wrap, and that points to the same layer that was there before, right? But this wrapper, let's take a look at what do we have in the wrapper, right? So you would see that you have access to an input quantizer, an output quantizer, and param quantizers, right? So let us take a look at what this input quantizer is. And so it is some object of type post-training tensor quantizer. But if you look at the properties of this, you can see that you have something called enabled, a scheme, and then some methods, but also like a round mode and other things like bit width and so on. So let's say, let's take a look at some of these things, right? So in this case, it turns out that for this particular layer, the input quantizer is actually not enabled. The enabled is false. Whereas if we go and change this to the output quantizer, I bet you that that is enabled, right? So that is true. Now in this output quantizer that is enabled, we could start to look at what is the bit width set for this, right? So we had by default passed in 8 bits for outputs, and the same thing we could do for parameters. So the param quantizers is actually a dictionary, and the key of the dictionary is the name of the parameter, and then once you go to the key or the value, it is another object of the same type, post-training tensor quantizer. So you would have access to exactly the same things, and so you could basically say, is this enabled? And you will see that yes, it is enabled. What is the bit width of it? We can look at the bit width of it, and it's also set to 8 bits. Okay, good. So now you can inspect things at this level. So not only can you inspect, but you can actually set things at this level as well. So for example, if you wanted to say, I want let me run the whole model in 8 bits, but there is one particular layer, that little bit problematic layer. Let me try to increase the bit width of it. And you can do that. So for example, what you would do is, let's say you wanted to do that for the output, you can set the bit width simply like that. Let's say for the parameters, for the weight parameter, you want to put it into symmetric mode. So what this would mean is when the encoding, the min-max values are calculated, they are centered around 0. That's symmetric. By default, it would use asymmetric. So asymmetric gives you a little more resolution because you don't have to center it around 0, but it comes generally in hardware, it comes at a cost because you have to, there are some cross terms that you need to keep track of as you're doing, especially matrix multiplies with these asymmetric encoded tensors. So, I'm just showing you some things you could do, right? So this, what I'm trying to motivate to you is like you have a whole lot of things that you can do, and you can change knobs at a very granular level. And, this will give you a lot of options to play with and truly try to understand your model. And then every time you do this, you can run the compute encodings one more time and get an evaluation and see what that did. Right, so you can actually do a bunch of experiments this way. Okay, the other thing I would like to sort of show you is like you have the simulation, so you could actually print the simulation. It has a printy printer associated with it, and what this pretty printer would do is it's going to print some of these information out for you. So it's going to take like, hey, this was a layer 4.1 con 2. It says the input is unquantized, meaning it is disabled. The parameters weight is quantized, output is also enabled, and bit width is 8, encoding present is false, meaning it has not, we haven't gone through a compute encoding yet for this layer, because we ran it all again and we stopped at that point, right? So we haven't actually called the compute encoding. So let's look for that layer that we actually changed. So this was, if I remember it right, layer 1 0 con 2, so that it was this layer. And if you see, like we have changed the output bit width of it to 16 bits, right? So this is another way of like looking at what is going on in your model. Obviously you could write your own routines to iterate over all these different layers and look at different parameters and so on and so forth. So I think that was all I wanted to cover today. So it's fairly simple to use this quantization sim model, and it gives you in very simple steps simulated accuracy for running on quantized hardware. So I hope you found this video useful, and I hope that you get a chance to view the other videos in this series. So there will be another video on quantization specifically where we would talk about these techniques called cross-layer equalization and bias correction. Together they are sometimes referred to as data-free quantization, and these are some very interesting, powerful techniques that will actually help some very hard to quantize models. So see you later. Thank you.